This video is over dilations. This is pathway 5C. First of all, what is a dilation? It is something that looks like this. Here are two examples of dilation. So you might notice that the giraffe has a little baby giraffe next to it. It's like a miniature version of the giraffe. This is almost like a real life scaled down version of a normal sized giraffe is a baby giraffe, right? This is called a dilation. Another example of a dilation is when your pupils dilate. So this is an example of a pupil in really dark places. So sometimes if eye doctors have to dilate your eyes, just for like eye surgery or something like that, they might do this to one eye. It's your pupil, and everybody has pupils, and they dilate when they want to let more light come in. So everybody's eyes actually have a pupil pretty this big when it's really, really dark. And then when you go into somewhere that's really, really light, like outside or in a really bright room, your pupils will dilate and shrink until they're really small. So a dilation can either be enlarging or reducing in size. It does not change the shape. No matter what happens, your pupils stay a circle, a perfect circle, and they either get larger or smaller, but they stay a circle. Okay, so here are some other examples of dilation. So when you go get a fountain drink from the corner store or a fast food place, a medium, small, medium, large are all kind of dilations of itself. Here is a dilation of a tiger. It kind of starts from like something at the center and it grows. A dilation of a puppy kind of shows you the different dimensions that it could change to. So it was 1 meter, oh my goodness, and 2 meters. It kind of changed in size, kind of doubled it looks like, because it was 1.5 and then it changed to 3. Kind of tells me it doubles. And here's what a dilation looks like on a graph. It has a small triangle and then it changes to a big triangle. I can tell that this is the one it changed to because of those little tick marks up there. Those mean prime. Those tell me that something changed. All right, let's get into the notes. So first of all, you have notes that say similar figures on them. I want you to write at the top of this paper that similar figures are figures that look alike because they have a dilation. We're not going to write all that, but that's what I was meaning. Okay, so a dilation is something that changes the size of the picture, not the shape. Shape stays the same. The shape stays the same, but the size is the one that's different, and that's why we call it similar. Similar means alike. It doesn't mean perfectly alike. Congruent would mean perfectly alike. However, similar just kind of means kind of alike. So similarity is two figures are similar if the second one can be obtained from the first by a sequence of transformations and dilations. So we do know the word transformations. That would be something like translation, rotation, reflection. And dilations are our newest transformation and our final transformation for the unit. So let's look at this triangle ABC. It says that it is similar to triangle DEF. Now we're going to draw DEF. Also, there's no equal sign right here because, like I said, it is not perfectly equal. It is not going to be the exact same size, but it will be the same shape, which means it's similar. I'm going to draw a triangle that is the exact same it looks like the exact same triangle, just a bigger version. It even looks so much the same that the angles are in the same spots. So instead of calling it ABC, I'm going to call it DEF, just like they told me to. And I'm kind of lining up my angle. So I still have this right angle, next to the angle that kind of fits. And then this really, really small angle kind of over here. Now, if yours isn't perfect, that's okay. We're just kind of trying to show you that the angles in dilations will never change in similar figures. The angle measures are never going to change. As in, this is still going to be a 90-degree angle no matter how big or how small we make this triangle. So let's make a couple other examples of a similar figure with this same triangle. What if I drew a triangle really, really tiny like this? That is still similar to the triangle I drew. It's just a shrunk down version. So these are examples of dilations, similar figures. Here's another example. What if I drew a really big triangle, but I drew it upside, like kind of rotated a little bit? Because remember, it said we could use the transformations if we wanted to. I'm going to put the corner kind of like it was here, but almost like it turned to where this should be D, this should be E, and this should be F. All right, we're just getting an idea of what similar figures look like. Now let's move on to actually talking about their relationship and how they relate to each other. So proportional relationships are was a topic that we talked about in graphs a long time ago with lines, and the situations in proportional relationships went up by a certain number, and that's actually what's going to happen here too. So I want to give an example, 8, 6, and 2. We're going to pretend that this triangle has the side lengths of 8, 6, and 2. And then the next triangle is going to have the side lengths of 4, 3, and 1. Now you might be able to tell a pattern here, and if I said what happened to the triangle, they are similar figures, and we will for sure check that they're similar in a second. But there has to be some type of shrink or some type of enlargement happening. And if it were going from this triangle down to this triangle, we would be shrinking, and it looks like the numbers are being cut in half. So half of 8 is 4, half of 6 is 3, and half of 2 is 1. So it looks like we were cutting it in half, which it said it would be between a common ratio. So our ratio of that would be a half. However, if we were going from this triangle to create this triangle, we would be jumping up by 2. So 4 times 2 is 8, 3 times 2 is 6, and 1 times 2 is 2. So it really depends on which way you're going, but we will be, someone's at my door. I'm videoing. Sorry, okay. So it will depend on the size lengths and how it changed to where you can figure out what is really happening. Here's some information on talking about scale factors, which we will get more to tomorrow. Just the fact that there should be some type of number that is going to get bigger, create a bigger picture or a smaller picture. All right, let's talk about these proportions though. I said these were proportional, and we can kind of see this in our brain, how these should kind of equal each other out. As in, I said that 8 over 4 was 2, right? It should equal the same thing as 6 over 3. I'm taking the numbers and seeing how much they would have taken if they were dividing or multiplying by a certain number, all right? 8 over 4 is 2, 6 over 3 is 2, so these fractions are proportional. Now, if we're trying to set proportional fractions together and see if they're proportional, determine if they're proportional, we should set them up like this, and then we would use the method of cross multiplication. This is an old method that helps us remember, or helps us figure out if the fractions are proportional. So let's take an example down here. Remember, we kind of cross multiply to see what their answers are. So I'm going to use different colors just to kind of keep myself organized. I see that these two triangles look super similar. They look like one is just a dilated version of the other. Let's see if that's true. The top number up here is 8, and then we have 12. And I highlighted both of these sides in green because these are called corresponding sides. So I'm going to do 8 over 12. I did the small triangle number on top and the bottom triangle number on the bottom. But of course I kept the corresponding sides together. So then I'm going to use my different color to kind of highlight those lines right there. And I'm going to set this proportion equal to another fraction. I'm going to do 6, and that is actually an 8. 6 over 8. So I pay attention to kind of how I formed the fractions. I took 8 and 12, which were the corresponding sides, and I kept them in the same fraction. I also did the small triangle over the big triangle, which means over here I have to do the small triangle number over the big triangle number, which is what I did. Okay, as long as your fractions are being organized correctly, at least organized with the same numbers, it will work for you. Okay. Now we are going to work on the cross multiplication. We're going to test these fractions to see if they're equivalent, or if they are proportional. 8 times 8 is 64, and 12 times 6 is actually 72, which those numbers are not the same, which tells me that these shapes are not similar. Which means that they look the same, however, they are not the same. They tricked us just by a little bit that these don't exactly match up to each other, okay? They're not a dilated version. There's no scale factor because these fractions aren't proportional. So I'm gonna move on to the next triangles. I'm gonna set up my fractions again, but this time I'm gonna set up them in a different way. And here's how. First of all, these are dilated version. One of this looks like a dilated version of the other. It's just flipped upside down. So don't let that trick you. I'm gonna highlight 2 lines in 2 different colors from the same triangle. And this is what I'm gonna do. 8/10. I'm gonna set it equal to another fraction, but on the next fraction, I'm gonna need to use both of these numbers from the second triangle. However, I have to make sure that I put them in the right place. On the top, I used the 8, which was the green color, which means I have to use the green color on the top, the same line. Remember, these are called corresponding sides. They are the same side of the shape, even though it is in a different, or even though it looks like it's in a different, the shape looks a little different. Okay, which means that the 15 is a corresponding side with the 10. I meant to put 15. Sorry. And then I will cross multiply to see what the answers are. So this is 120, and 10 times 12 is 120, and 8 times 15 is 120. These are similar because the proportional fractions work. As long as you can set up your fractions correctly, they can kind of work either way. As long as you have things in the right spots, you're good to go. Let's move on to your second page. We have 2 more examples, and then we will be done. So we have quadrilateral ABCD. We're going to find it's similar to the other quadrilateral, WXYZ, and we're going to set up a proportion to find the missing measure. The missing measure is here. And if I were trying to set up a proportional fraction, I do know that this line and this line are together. Excuse the boxes up at the top. I'm actually not going to use them. I'm going to set up proportional fractions like this. I do want M to be my first one. You could honestly set these up however you want. I'm just going to do it this way. So I'm going to do 12, M over 12. M over 12. Which means that on my second fraction, I'm going to need to, since this was from the big quadrilateral, I'm going to need to use a number from the big quadrilateral also. So I'm going to use 15. Now, this number has to be from the smaller quadrilateral, which needs to be a corresponding side with the orange line that I just drew. And we will be cross multiplying here. 12 times 15 is 180. And we cannot cross multiply these two because M and 10 multiplied to each other just make 10 times M, or 10M. So if these two are supposed to equal, the next step that I would do is divide. 180 divided by 10 equals 18. So at this point, I would cross multiply and then divide. You might remember these steps from earlier versions of this stuff in your math classes. All right, one more example, and I'm going to draw a picture. It says a fire hydrant is 2.5 feet high and casts a 5-foot shadow. So let's pretend that Miss Garza's fire hydrant is super great, and I literally have no idea how to draw a fire hydrant. So that's my fire hydrant, and it casts a 5-foot shadow. The fire hydrant is 2.5 feet tall, and the shadow is 5 feet. And then it's standing next to a street light. I don't know, guys. We're just going to say that that's my street light. My street light casts a shadow of 26 feet. And it says, let H represent the height of the street light. So let's set up some proportional fractions. Let's use this number and this number. Let's just 2.5 over H. Notice I put my missing piece in a different spot. You are totally allowed to do that as long as you can get your fractions to set up correctly. The second fraction, since I use both of the corresponding sides that go straight up, I'll use the corresponding sides that go straight across. Now on the top, I put the number from the small picture, so I'm going to keep it that way. And on the bottom, I put H from the bigger picture, the street light. So I'm going to keep it that way too. At this point, you will be cross multiplying. 2.5 times 26 equals 65. And the last thing you would do is take this extra number here and divide your answer. The answer was 13, so 13 feet should be how tall the light is.